Good morning, good afternoon, good evening, whenever you're watching this video. I hope you're doing good. We're going to get into a topic that I would probably consider the meat of the probability that we're going to cover. Okay, so I anticipate this section taking 2 days. Now, I'm going to give all the notes right now, and so I'm just going to tell you I anticipate this section taking 2 days in class. So we'll see how it all plays out. So permutation combinations, we're going to get to that, the concepts in just a little bit, but I want to build something in order to understand where those concepts come from. So I got this first problem here that says create a tree diagram that would illustrate the number of outfit options that one would have if 2 types of pants, blue jeans and black pants, and 3 types of shirts, red, green, and blue. Now I know that you guys have probably done this in, I don't know, 7th, 8th grade math, maybe even before that. But here's what a tree diagram is if you forget and how to work it out. So the tree diagram, I'm going to go ahead and put down blue jeans, okay, and then we have black pants. And so from each of these, I could choose a different color shirt, so red, green, and blue. So the tree part kind of spans out like this. Red, green, and blue. Okay, blue jeans, blue shirt. All right. And you also have the red, green, and blue for the black pants as well. All right, so from there, you've got basically 6 different outfits. You've got blue jeans and a red shirt. Okay, you've got blue jeans and a green shirt. Okay, so the reason why we end up doing the tree diagram is so we can easily see all the combinations that are taking place here, all the possible options we could have. Okay, and then you have the black pants. And I'll just go ahead and do this for the next 2. Red shirt, green shirt, and blue shirt. Okay, so you've got those 6 different options, and so that kind of leads us into the next concept, which is, you see it right down there, the fundamental counting principle. And the fundamental counting principle basically says this: if you have 2 options and then you have 3 more options of something else, when you bring those 2 together, it will make 6, okay? So if I would have had like 5 different pairs of pants and 6 different pairs of shirts, there's 30 different outfits that I could come up with, 5 times 30. Now the fundamental counting principle itself, I'll go ahead and read it off here, and so you've got it itself written down. It might be a little technical to understand, but we'll see. If event M, so that's how it starts out, if event M occurs in M ways, and event N occurs in N ways, then event M followed by event N can occur in M times N ways. Okay, you may have to rewind that to listen to it so you can jot that down, but it goes back to what we just said. The product of the 2 gives us the total number of options you have there. Okay, so as we look at example 1, you can probably just go ahead and work through those problems faster than I can even talk through them, and then you can double check yourself. But here's what we have for example 1. It says here, a deli offers a lunch special if you choose one from each of the following types of sandwiches: side items, and drink choices. How many different lunch specials are possible? And so as I look at that, and we considered the previous problem, you have 1, 2, 3, 4, 5, 6 different options for sandwiches. You've got 4 different options for sides, and you've got 5 different options for a drink. If you multiply those all together, you're going to have 120 different options for lunch. Okay, or for the lunch special. All right, so you know, feeling pretty good if I'm going to that place. It looks like a small menu, but you realize that there's a lot of options there you can come up with. B, cybersecurity. Suppose that a computer generates the passwords that begin with the letter followed by 2 digits, like R38. The same digit can be used more than once. How many different possible passwords can the computer generate? Okay. Well, let's start with each one of these options here. When you think of yourself for the letter, how many options would there be? Well, there's 26 letters in the alphabet, so that would be your first one. Then you think to yourself, the 3, how many options would there be for that first digit? Well, there's 10 different options. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? There's 10 of them there. And so I'm going to put down 10. And since these digits can be reused, used more than once, I'm going to put down 10 again. And so in the end, well, we have 2,600 different passwords that we could put down. So I guess when you think of passwords these days, I mean, my goodness, have to be at least 8, letters long. You have to have a capitalization. You got to have, maybe some sort of symbol, And so, man, it's just millions, billions of options there. So, letter C. The lock on the basketball cage in the gym is 4 digits ranging from 0 to 9. This is a true story. I mean, if you go to the gym, you've got 4 digits ranging from 0 to 9. How many possible combinations does the lock have? Okay. Well, the first one is, if I were to go 0, 1, 2, 3, okay, you've got 10 for that first one. You've got 10 for that second one. You've got 10 for that third one. And you've got 10 for that last one. So in the end, when you multiply those all out, just to protect the basketballs in the gym, there are 10,000 different combinations, different possible lock combinations we could put down there. Okay? So, I feel pretty good, unless you know the combination. So, looking at the next section here. Okay. It says, find the number of permutations. Now, we don't know what a permutation is quite yet, but let's see if we can think this through. How many ways can you arrange a book? Can you arrange 12 books on a shelf? Okay. Well, when you think about that, with the 12 books, if I pick up one book, so I've got 1 of 12 here, so I'm going to put down 12 for that first book. Okay. Now, that next book, I can't pick up 12 more. Okay, using that fundamental counting principle, it's not going to be 12 times 12 because I've used up one of those books. Okay, and so now I've only got an option of 11 books. Okay, for the third book, I pick another one up. Now I've got 2 less, so I can use it times 10. And I think you're starting to see the pattern here. Fourth book would be 9, fifth, 8, sixth, 7, and all the way down to 12, down to 0, I should say. So we end up with 6, 5, 4, 3, 2, 1. Okay? And so what's important to understand about permutations, okay? is that the order does matter, okay? The order matters. And so in which I pick up that first book cannot be used again. And that's why the order matters. If I pick up the second book, I can't use that one again either. So order matters. And so as a result, when you work all this out, you end up with, oh, I actually didn't work this one out yet. And so I'll do that real quick. All right. Oh my goodness. A big, big number. 479 million 1,600 different ways to arrange 12 books on a shelf. Okay. All right. Now I will tell you this. The way I just did the calculation, I didn't actually type in all 12 of those numbers there. This right here is called a factorial. So if I go ahead and take 12 factorial, that means that we're multiplying 12 times 11 all the way down to 1. Okay? If I do 5 factorial, what I'm doing is 5 times 4 times 3 times 2 times 1. All right? And so very simply, I can just do that. Now, how do you type in a factorial into your calculator? Well, you can go to the math button and then to the probability. And then I believe it's down like 3 or 4 spots if you have a big calculator, a TI-83, TI-84. So that's one way you could do it. Or you can type it all in. You're going to get the same exact answers. I'm not sure if the TI-30s, the smaller calculators, have the factorial. I'd be surprised if they don't, but I'd have to look it up, and I haven't seen it recently. So, for the music, it says you download 8 songs onto your cell phone. If you play the other songs using a random shuffle option, how many different ways can the sequence of songs be played? So I guess I'm under the impression that with the random shuffle option, once it's used one of them, it doesn't go back to it till all the other ones have been played. Okay? And so randomly selecting one of those songs would be one of 8. And then I've got 7, and then 6, and then 5, and 4, and 3, and then 2, and then 1. And if it's still playing, I'm assuming it just starts all over. Okay? Again, randomizing everything. But again, this is what we would consider 8 factorial. Okay? And the probability, not the probability, sorry, the number of permutations that we would have here would be 40,320 different permutations, different songs that we could play. All right, so a wide number of possibilities there. Now for letter C, it says using the information from the previous problem, you only have time to listen to 3 songs. How many different ways are there to listen to these 3 songs? Well, I hope that you're seeing that you have to start at this end. Okay, the first option was there was 8 total songs to choose from, and then there were 7, and then there were 6. So what we're actually looking at is this right here. 8 times 7 times 6. Okay? But you could also think of it in this manner, and this is actually going to lead us to our permutation formula later on. And if you go ahead and take the 8 factorial, and if I go ahead and subtract 3 from the 8, because I'm choosing 3, let me write that again. 8 minus 3 factorial. That would be down here. Okay? What we would have left over is this right here. Okay? So your 8 times 7, 6, 5, 4, 3, 2, 1. Okay? And then on the bottom, 8 minus 3 is 5, so you would have 5 factorial down here. And if we cancel out these, what we're left with is what we started with over here, okay? And so I actually kind of, in doing this right here, gave away the permutation formula, all right? And we're going to get to that in just a second. So before we do that, I want you to jot down the definition for permutations, which is this: an arrangement of items in which the order, and I would probably capitalize the word order and maybe even underline it, put it in a box, because that's really important. The order of the object is important, okay? The order of the object is important, okay? Now, as far as the factorial notation down there, guys, you can just put down an example for yourself, like 4 exclamation point, 4 factorial equals 4 times 3 times 2 times 1, and that's completely fine with me. Okay, I just need to make sure you understand what a factorial is. Okay. Now, in looking at example number 3, here's what we have. Finding a permutation. It says here, the FFA election, permutation notation. We have that, don't we? I got to go back up there. I went one beyond. Okay. What is permutation notation? Okay. I'll write this out here. The number of permutations of n times of a set of arranged R items at a time is NPR. So if I write this down, you don't have to write it down. I was just reading off the definition for you. So there's a little number, a P for permutation, and then another number over here. Again, they're smaller, okay? What this means is that the N over here is the total possible number of permutations if the whole thing was an option, okay? If all of them were an option, that would be your answer, okay? The R is what we're selecting from that option. So in the previous problem, as you looked at that, we had the 8 minus 3 factorial, okay? And so the 3 was the number that we're selecting from that. So I'm going to go ahead and do n minus r factorial, okay? And, you know, like I said, we already saw that on the previous example. That's just the formula that you're going to use for a permutation. So how does this play out? Well, in the elections, the FFA is electing a president, vice president, and treasurer. So the question I would ask you before we get going in this problem is, does the order matter? If I select a person to be president, can they then be selected as vice president? And the answer is no. They've been pulled out of the possible number of options for vice president. If I select a vice president, that person cannot be selected as treasurer, okay? And so on and so forth. So how many different ways can the officer be chosen from the 10 members? So what we're looking at here is this. If I was to set this up in permutation notation, we have 10 possible members, and we're choosing 3 from that. And so if I set this up using the formula up above, 10 factorial over 10 minus 3 factorial, okay? Now, if we work this out, you should get something like this in the numerator. I want you to practice this. The 10 factorial should give you 3,628,800. So make sure you know how to plug that in your calculator and get that number out. The 10 minus 3, or 7 factorial, is 5,040. And so in the end, when you divide those two out, you end up with 720 different ways that you could choose a president, a vice president, a treasurer from a 10-member committee, okay, from the FFA. All right. Letter B, 12 swimmers compete in a race. How many possible ways can the swimmers finish first, second, and third? Okay. Now, if a swimmer finishes first, can they finish second? No. If a swimmer finishes second, can they finish third? No. And so order does matter here. And so we're just going to go ahead and do, there are 3 swimmers, vying for, there are 12 swimmers vying for 3 spots. And so in the end, we have this right here. Okay? And so if you work that out, and I would encourage you to do so, there are 320 different possible ways that those 12 swimmers could end up first, second, and third. Okay? Didn't think there were that many options there. All right. Taking a look at the next section. Combinations. So here's what I want you to see about a combination. Using the combination formula. Now, I haven't introduced the formula yet, but we're going to take a look at it here in a second. Okay? And so if we look here, it says, suppose that you choose 4 books to read on summer vacation from the reading list of 12. How many different combinations of the books are possible? Okay? And so in this case, when you're using a combination, okay, it really doesn't matter. Let's actually go down and define the definition for a combination down below here, okay, down here. And so I would write this down: a selection of items in which order is not important. Okay, a selection of items in which an order is not important, and I would emphasize order and not, as opposed to order and is. Okay. So the question I have for you in looking at this first part would be this: does it matter what book you read and when? Okay. As long as these 12 books aren't a part of a series, it doesn't matter which book you read and when. All right? And so as a result, I'll just go ahead and kind of give you the background information on a combination. So let's say we have, I'm going to write down book combinations. Okay, and let's say we use 3 of them. Okay? And so let's say we have book A, book B, and book C. Now, how many possible ways could I arrange that? Well, if the order matters, it would be ACB, ABC, BAC, BCA, CAB, and CBA. Okay, let me make sure I've got all of them there. 1, 2, 3, 4, 5, 6. Yeah. Okay. Now, according to the permutations, all of those count. So all of those would be 6 different ways. Okay. The problem is, if the order doesn't matter, then these would all be considered one combination. Okay. All that's just one combination. And so because of that, we're gonna severely cut down on the number of options here. And so if we take a look here, I'm going to go ahead and do this. If we have 12 different books to choose from, that's going to be 12 factorial. Okay? And if there are 4 books that I'm choosing from that, I'm going to do the 12 minus 4 factorial. Okay? So far everything looks great. Okay? The problem is this: with these 4 books here, okay, each one of these would be considered one combination, kind of like over here. So I'm going to go ahead and put this 4 on the outside over here. And so in the end, I have this. I have 12 factorial minus 12 over 4 factorial, which would be this. 12 times 11 times 10 times 9. Yeah, so there's 4 of them there. So that would be this right here. Okay? But we also have to include this right here. So I'm going to put this over 4 factorial. Okay? So I didn't write that all out. I just tried to show you, if I was to take 12 factorial over 8 factorial, that would leave me with this right here, and then over 4 factorial. And this is what we call a combination. And so there are 495 combinations of how I could read those 4 books from that list of 12. Okay? All right, so let's take a look at letter B. Service Club has 8 freshmen. 5 of the freshmen are to be on cleanup crew for the town's annual picnic. How many different ways are there to choose a 5-member cleanup crew? Now I did make a little note here. Since all the members have the same title, order does not matter. All of them are under the cleanup crew title. Okay? And so what we're going to end up doing is this. We've got 8 freshmen. So that's the total number of possibilities with 8 people. Okay? 5 of the freshmen are going to help out. So I'm going to say the number of permutations would be that. But since order doesn't matter, I'm going to go ahead and do this right here. Okay? And so in the end, if I do just this part right here, you end up with 8 factorial over 3 factorial, which would be 8 times 7 times 6, 5 times 4. 1, 2, 3, 4, 5. Yep. And that's over 5 factorial. Okay. And so in the end, we end up with 336 different ways for a 5-member crew to be chosen from an 8-member crew. Okay? Again, order, is it important or not with this certain problem? So in the next one, the combination notation, you can just write this down, that we have N, C, R. Okay? N is the total number of population. R is how many we're choosing out of that population. Okay? And so we end up with this. The formula that I hope you can see right here. So if I was to do this one, it would be this, 8 and 5. So it would be R factorial and then N minus R factorial. Okay? All right, now, in looking at example number 5, the real question as you look at the different types of probability is, can I identify which one I'm working with? Okay, it's not the easiest thing to do. So here's letter A. A college student is choosing 3 classes to take during first, second, and third semesters from the 5 elective classes offered in his major. How many possible ways can the student schedule the classes? Okay, so the question here is this. Does order matter? Is order an important part of this problem? Well, I'm looking here. If it's offered in his major, the elective classes are offered in their major, oftentimes, guys, the order must be followed. So if you start taking math courses like in college, mine went Calc 1, 2, 3, and then it went on, and I can't remember the next couple. It was differential equations, linear algebra, analytic geometry, those type of classes. And so when we look at this, the order is important. So I'm going to go ahead and say that this is a combination. Classes in one's major have an order that must be followed. Okay. Oh, I see. But if they're elective classes, this is the important part here. I almost misread this. If they're elective classes, you can take the electives at any time, okay? And so electives are kind of outside your major that can help you with your major sometimes. And so I elect to take them because they're kind of fun. So as a result, I'm going to use the combinations here because order isn't, I can take one, the one class isn't imperative for the other class. And so what we have here as a combination is that we have 5 different classes to choose from, and we're going to take 3 of them. Okay? All right. So, with that being said,